So in set theory, given two sets x, y, the Cartesian product of x and y is the set of all ordered pairs of the type xy where little x is in big X and little y is in big Y. So you can think of the Cartesian product, it's denoted as x cross y, and you can think of it as the set of all pairs of the type xy such that little x is in big X and little y is in big Y. Let us look at an example. Let's A be the set containing x, y, and z, and let's B be the sets containing 1, 2, and 3. Then the Cartesian product A cross B will be the sets of all other pairs taken from A and B. So we'll have x1, x2, x3. We can also have y1, y2, y3, and we can have z1, z2, and z3. That's A cross B. That's a Cartesian product. We can also have other more interesting examples. So for example, if you take R cross R, this is the set of all order pairs xy such that x is in R and y is in R, and this actually corresponds to a plane. This is R cross R can be really regarded as R2. This is usually what we call R square. You can also have, for instance, R cross N, which would be the set of all order pairs of the type xk, where x is a real number and k is a natural number. So note that if x and y are finite sets, and let's say that x has m elements and y has n many elements, then the Cartesian x cross product x cross y, or the Cartesian product of x and y, has m times n elements in it. So the cardinality of a Cartesian product is the product of the cardinality of the two sets. Notice also that one can define, so given sets x, y, and z, we can define x cross y cross z as the set of all triples of the type x, y, z, where little x is in big X, little y is in big Y, and little z is in big Z. Okay. Now, given two groups, G and H, let's consider G cross H be the sets endowed with the following operation. We'll say that x, y combined with u, v is the element xu, yv. So this product is essentially, this new product is obtained by taking the product component wise. So you'll take here x times u, and then you'll have y times v to get the second component. So it turns out that this structure has the structure of a group. So in other words, this operation is associative. It's also clearly the set. So the point is, given x and u in G, and let's say y and v in H, clearly xy combined with uv being xu and yv has to be in G cross H, since xu is in G and yv is in H, and this is due to the fact that G and H are groups. So because these groups are closed under the respective operations, then this new operation is also the Cartesian product G cross H. The Cartesian product of G and H is closed under this new operation. Also, given x, y in G cross H, notice that if we combine x, y with the inverse of x and the inverse of y with respect to the respective operations, we'll get x inverse, y inverse, and the first here will be the identity in G, and this will be the identity in H. And then similarly, if you take x inverse, y inverse combined with xy, we will also get x inverse x, y inverse y, and this will be EG and then EH. Now, to conclude that these elements are inverses of each other, we'll need to show that this element here is the identity in G cross H, and this is certainly the case, since xy combined with EG EH will be XEG and YEH, which is X and Y. And similarly, if we take EG EH combined with XY, that will give us EG X EHY, which is also XY. Thus, EG EH is the identity in G cross H, and for any x y in G cross H, we have that x inverse y inverse is the inverse of xy. Thus, one can conclude that G cross H endowed with the given operation is indeed a group. So let's look at an example here. Let's consider Z2 cross product Z4. So this set contains element of the type Kj, where K is in Z2 and J is in Z4, right? So so the operation here is the following. When we have X, if you have, let's say, K1 and J1 added to K2 and J2, what we expect here is going to be K1 plus K2 mod 2, because we in this component, and then we'll have J1 plus J2 mod 4. That is our operation here. So Z2 cross Z4 is a group of order 8, since 2 times 4 is 8, right? Okay. Let's consider another example. Here I would like to prove that Z3 cross Z2, Cartesian product Z2, is isomorphic to the cyclic group Z6. And to this end, I will construct an isomorphism. So let's be a map between Z6 and Z3 cross Z2, where we'll say that phi K is K mod 3 and K mod 2. Okay, so we need to show that this is a homomorphism, right? So for K and J in Z6, if we do the operation K plus, and for me here this addition is really modulo 6 J, that will be K plus J, right? Whatever this is, mod 3 and this one here will be K plus J mod 2. Okay, but then it actually turns out that this here will be K mod 3, and we'll have here K mod 2, and we'll have here J mod so we'll have here K mod 2 plus we'll have here j mod 3 and j mod 2, but the first addend is phi of k, and then the second one is phi of j. Right, so again, maybe it's not completely clear why the second equality is true, so maybe you want to take some time here to really understand for yourself why this here is indeed true. But in any case, the third equality tells us that phi is a homomorphism. Okay, now I claim that phi is injective, and to see this, suppose that phi of k is equal to phi of j for k and j in Z6. So that means that k mod 3 must be equal to j mod 3 and k mod 2 will be equal to j mod 2. Why? Because phi of k is precisely k mod 3 and k mod 2, right? And phi of j is j mod 3 by definition and j mod 2. So in any case, looking at this equality, then this tells us that k minus j has to be equal to 3l, and at the same time k minus j has to be equal to 2m for some integers l and m. So that means that k minus j is a multiple of 3, and also it is a multiple of 2. So if you have a number which is both a multiple of 3 and a multiple of 2, as such, k minus j must be a multiple of 6. Right? So without loss of generality, we may assume that k is greater or equal to j. But if k is greater or equal to j and k, since k and j are both in Z6, and the fact that k minus j is a multiple of 6 shows that k minus j has to be 0. That's the only way this is possible, right? So consequently, k must be equal to j, and the map is injective. So this is an injective map. So we have a monomorphism. We have an injective homomorphism. Now it remains to show that the map is surjective, right? So next, since phi of 4 is equal to what is phi of 4? Phi of 4 is gonna be 1 0, right? Because we have 4 mod 3 and then 4 mod 2, that'll be 1 0. And what is phi of 3, phi of 3 will be 3 mod 3 and 3 mod 2. That's 0, 1. Notice that 1, 0 and 0, 1, both of these two together generate Z3 Cartesian product Z2, right? So if you can show that the generators are in the range of the function, so then every element in this group will be in the range of phi, right? So in other words, so these two will generate any element in the range. So the range has to be everything. This Z3 cross Cartesian product Z2 must coincide with the range of the map. And perhaps another way to see this is also to maybe just completely exhaust all possibility, right? Through the map phi, 0 will go to 0, 0, 1 will go to 1, 1, 2 will go to 2, 0, 3 will map to 0, 1, 4 will map to 1, 0, and 5 will map to 2, 1. So you can see that this map here is clearly surjective. So since phi is a bijective homomorphism, it is an isomorphism. Consequently, Z6 is isomorphic with Z3 Cartesian product Z2 as desired. Okay, so we will show in this example that although Z4 and Z2 cross Z2 are both abelian and they're both of order 4, they're actually not isomorphic. And the best way to see this is to look at the Cayley diagram. So let's first start with Z4, which contain 0, 1, 2, and then 3. Right? So we'll have here 0, 1, 2, and 3. Let us look at the generator, which 1. So what will happen is if you start with 1, 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 1 is 4, which is 0, 0 plus 1 is 1, and then this is essentially everything. So clearly we already knew that Z4 is cyclic and is generated by 1. Now let's consider Z2 cross Z2. We'll have here 0, 0, 1, 0, 0, 1, and 1, 1. And let's look at the Cayley diagram of so we have 0, 0 here. We'll have 1, 0. We'll have 0, 1, and we'll have here 1, 1. Okay, so I'm going to start with so here we'll start with the 1, 0 here. So if I add 1, 0 to 1, 0, what's going to happen? If you take 1, 0 plus 1, 0, that'll be 0, 0 with respect to this group operation, right? So we are here, and then if I add 1, 0 to, if we take 0, 0, and then you add 1, 0, we get 1, 0. Okay, and it keeps doing ping pong essentially in between these two elements. So we can't generate the entire group. with just 1 0. We need a new element. So let's pick, for example, 0 1. If we add 0 1 to itself, we get this element, right? And then if we add again 0 1 to 0 0, we get 0 1. Okay, now what happens if we add 0 1 to this element? If you add 0 1 to this element, we get this. And if we add 0 1 to it again, so if we take 1 1 plus 0 1, we'll get 1 0, right? So okay, now what happens if we add say 1 0 to this element? If we add 1 0 to this element, we get this set. And if we take 1 1 and then we add again 1 0, we get 0 1. Okay, and so on. So you can see here that even if we take the generators 1 0 and 0 1, which will of course generate Z2 cross Z2, there is no single element which will generate the entire group. So this analysis shows that Z4 has an element of order 4, while in fact, if you try again with 1 1, you will see again that if you add 1 1 to itself, you get 0 0, right? So 1 1 plus 1 1 is going to be 0 0. So essentially the set Z2, Cartesian product Z2, has no element of order 4. Okay, so suppose by contradiction that there exists a map phi between Z4 and Z2 cross Z2, such that phi is an isomorphism. This will imply that, okay, so if you were to take phi of 1, that would be an element in Z2 cross Z2, right? And we know that since phi of 1, so okay, so if we take phi of 1 and then we get the identity, so suppose if, so there are two options for the first case. For the first case, suppose that phi of 1 is the identity element in Z2 cross Z2. In such a case, since every element, so if we consider f of n, then f of little n will be, right, essentially it's f of 1 plus 1, right, plus 1 n times. And since we have a homomorphism, this will be n times phi of 1, which will be n 0 0, which will be clearly 0 0, right? So thus phi is not surjective. Is not surjective. Okay. What if we assume for the second case, suppose that phi of 1 is an element of the type Mn, which is not the identity. Then we've seen that since every non-identity element of Z2 cross Z2 is of order 2, then it must be the case that phi 1 square, right, which would be Mn square, or if you prefer Mn plus Mn, we'll say, that must be 0 0 because this element has order 2. But if I guess I'll use instead here, we'll use we'll think of this here as phi of 1 plus phi of 1, right? But phi of 1 plus phi of 1 is phi of 1 plus 1, which is phi of 2. So this shows us that 2 is in the kernel of phi, and since 2 is not the identity, then phi is not injective. Contradicting that phi is a bijection. Okay, all right. So it's not possible to find to define an isomorphism between Z4 and Z2 cross Z2. So in conclusion, these two groups are not isomorphic to each other. All right. Definition. We can generalize the concept of a Cartesian product to n-many product. So if we let G1, G2, all the way till Gn be n many groups, we can define so recall that if we take G1 cross G2 and so on, this will be the set of all n tuples x2 xn, such that x1 is in G1, xn is in G, and so on. And then we will define this operation. Next, we define the operation x1 all the way till xn combined with y1 all the way till yn as the operation obtained by taking the product of each of them component wise, where it should be clear that all of these operations can be completely different, right? So this is the operation in the first group G1, the operation in G2 all the way till the operation in Gn. Okay, so we say that G1 cross G2 cross Gn is an external direct product of G1, G2, and so on all the way till Gn. So an external direct product is a way to put together a bunch of groups to get a new group structure. Let's discuss the following theorem. Let G be a group, and M and N are normal subgroups. Such that first, M intersect N is trivial in the sense that it contains only the identity, and two, M time N is equal to G. So you can get G by taking all possible products of elements in M and N. Then if this is the case, then G is isomorphic to the Cartesian product M cross N. They are not necessarily the same thing, but these two groups are isomorphic to each other. And okay, so the way to see it is as follows. We'll construct an isomorphism between these two maps. So let's define this map between M cross N and G. And this isomorphism is sort of given in the obvious way. Phi of x, y is going to be x times y. Okay? Then we hope that this is a group homomorphism. So given x, y, and z, v, if we compute phi of x, y combined with z, v, that will give us phi of x, z, and y, v, which will be precisely x, z times y, v, right? So essentially just x, z times y, v. Now, on the other hand, note that if we take phi of x, y combined with phi of z, v, we get x, y times z, v. And so to show that we have a homomorphism on our hand, we just need to check that these two things are the same, right? So to show that xz yv is xy zv, it suffices to prove, we just need to prove essentially that zy is actually yz. Okay, so that those two elements essentially are commuting. That's what but keep in mind that z is in M and y is in N, right? So they're not in the same group, but they're not in the same subgroups, I mean, but they both belong to G. Okay. In any case, so to this end, first we'll note that if you consider xy z inverse y inverse, this will be x, y, uh, no, so sorry, so this will be precisely this will be z, right? Okay, this will be z y z inverse y inverse, right? But then since m is normal, this shows that z y z inverse has to be in m, and since m is closed under its the operation, then z y z inverse y inverse is also in m. Okay, now similarly, using associativity, notice that if we can write z y z inverse y inverse as z y z inverse y inverse, and since n is normal in G, then y z inverse y inverse will be in n, and since n is closed again under the operation because it's a subgroup, will be in n. So this shows that z y z inverse y inverse is in m intersect n, but this contains only the identity. Consequently, z y z inverse y inverse has to be the identity, which shows that z y z inverse has to be y, and z y has to be y z. Okay, so zy is equal to yz, and then as a result, this shows that phi of xy and zv, which is xz yv, this will be equal to xyzv, which will be equal to phi of xy and phi of zv. Therefore, phi is a homomorphism. Okay. Now, we claim that the map was an isomorphism, so we need to show injectivity and surjectivity, right? So suppose so to show injectivity, let's look at the kernel. We just need to prove that the kernel is trivial. So suppose that phi of xy is equal to the identity for some xy in m cross n. Then that means that xy must be the identity and x must be equal to y inverse. So, but since y is in n, y inverse has to be in n. So, and since x is in m, this shows that both x and y are elements of m intersect n, which only contains the identity. So x must be equal to y inverse must be equal to the identity, and this means that x must be equal to y must be equal to the identity, right? So that means that the kernel of our homomorphism only contains the identity. and we can conclude that phi is indeed injective. All right, so now next we need to show that the map is surjective, right? So if we let x be any element in G, since Mn is G, there exists little m in big M and little n in big N, such that little x is equal to m times n. Next, phi of mn must be m times n, which is by construction x. Therefore, phi is surjective. So we have shown that phi is a homomorphism, is injective and is surjective, and then we can conclude consequently that M cross N is isomorphic to G. Alright, so let's suppose that G1 and so on all the way till Gn, let this be finitely many group. Okay, and let's consider the Cartesian product G1 cross G2 all the way till Gn. Then this element x1, x2, and so on, an arbitrary element in this Cartesian product has for order, the order of these elements is the least common multiple of the order of x1, the order of x2, and the order of xn. All right. Now, so to prove this result, let's suppose that S is the least common multiple of the order of this element, and we'll set T to be the order of this element. Then if we consider x1 all the way till xn power s, what would that be? Well, that's precisely this time itself s time, right? And then if we apply the group operation, so essentially it'll be x1 all the way till xn, x1 all the way till xn, n times, and this will give us x1 s, x2 s, and so on all the way till xn s, which will be eg1, right? Because s is the least common multiple, it's a multiple of all of these, or all of the orders. So this will be the identity in G1, this will be the identity in G2, and this will be the identity in Gn. Very good. Now, so automatically this shows that S has to be less than or equal to, T has to be less than or equal to S, right? Because T is the smallest element for which the power of this element is going to give us the identity. So, so T has to be less than or equal to S. Now, on the other hand, we see that if we consider x1t, x2t, all the way till xnt, this will be x1, x2, xnt, and then but by definition, this is eg1, eg2, all the way till egn, right? This shows that t must be a common multiple of the sequence of numbers x1, absolute value of x2, all the way till order of xn. Right, so okay, so thus S must be which is the least common multiple of this thing here. It has to be less than or equal to t. Right? It's a common multiple. T is a common multiple for all of these. And so because of that, the least common multiple has to be less than any common multiple. All right. So since S is less than or equal to T and T is less than or equal to S, it follows that S must be equal to T. Our next result is stated as follows. Let G and H be two groups which are cyclic. Okay. Then G, Cartesian product H, is a cyclic group itself if and only if the order of G and the order of H are relatively prime. In other words, the GCD between these two must be 1. Okay. All right. So let M be the order of G and let N be the order of H. That is, the order of this element must be M times N. And suppose that this is cyclic. And let GH be an element in G cross H, which generating be an element generating G cross H. Then what's going to happen if we consider GH power Mn over the GCD of M and N? This will be G m, right, power n over GCD of m and n, and this will be h n power m over the GCD of m and n. Now, this is clearly going to be the identity, right? Because the order of G is M, so this will be E, and then this will be the identity in H. Okay, so this shows that M times N, which is the order of GH, is less than or equal to M times N over the GCD of M and N. Okay, now, so but this means that, this implies that the GCD of M and N has to be 1, right? Because look at this and then look at that, which shows that M and N are relatively prime. Now, suppose next that G is generated by some element little g, and H is generated by some element little h. So we can write G essentially as this element and H as this element. Okay, so then and let us assume that the greatest common divisor of M and N is also 1. And if we look at the order of G and GH, it will be the least common multiple of these two. But this must be M times N, right? And so this factor is coming from our previous results, which we have already proved. And the fact, since M and N are relatively prime, then the least common multiple is essentially the product, right? And this is in fact the order of G direct product H. And this shows that G cross H is indeed cyclic. Okay, so in this example, we'll show that Z3 direct product Zn cannot be isomorphic to 27. And the reason why is simply because since the GCD of 3 and 9 is not 1, then Z3 direct product Zn, according to our previous result, is not a cyclic group. However, Z sub 27 is cyclic since it is generated by 1. Okay. So next, let's consider Z3 cross Z5. This group is actually isomorphic with the cyclic group Z15, since the GCD of 3 and 5 is 1. Both, I mean, these numbers are relatively prime. In fact, they're both prime. They're both primes. Z3 cross Z5 and Z15 are both cyclic groups isomorphic both cyclic group of order 15, I mean. And one way to actually construct an isomorphism, and I'll leave this as a homework. So the idea here to construct a homomorphism, so you define a map between Z15 and Z3 cross Z15, which will send a generator to another generator. So try to find what would you send. The generator of Z of 15 is 1. What would you send phi of 1 to? What would you send phi of 1 to? If you can identify what you've sent this to, then all you have to do next is write down an explicit formula for phi. B, show phi is a homomorphism. And then finally show that phi is a bijection. This will allow you to conclude that it's an isomorphism, and then the two groups are clearly isomorphic to each other.